Hello everyone. Today we start chapter 5 about continuous function. The goal is to define continuity and how to verify it. Throughout this section, we're going to consider function f from a subset A to a set of all real numbers R, and C is an element in the subset A. Here is the definition of continuous function. A function f is continuous at C if given epsilon greater than 0, there exists delta greater than 0 such that for x minus c smaller than delta in absolute value, then fx minus fc is smaller than epsilon in absolute value. This equals the epsilon delta definition of continuity. Indeed, there are several equivalent statements to this definition to give you several ways to understand this statement. The first equivalent statement is given in terms of a limit. A function f is continuous c even only if the limit of the function f of x when x approaching c is equal to f of c. Equivalently, we have a sequential criterion. For every sequence Sn in A, Sn approaching C, then f of Sn approaching f of C. Finally, we have a neighborhood statement. Given any epsilon neighborhood of f of C, there exists a delta neighborhood of C such that for x inside this delta neighborhood, then f of x must be inside the epsilon neighborhood. So this diagram here illustrates what's going on. We first specify a value epsilon which is very, very small. Then there exists a value delta such that for x within this delta neighborhood, then f of x must be within the epsilon neighborhood around the point f of c. So very, very narrow neighborhood. Now, the first consequence of that definition is actually a discontinuity criterion. That is, this is a negation of the continuity definition. And we saw several equivalent statements for continuity. The negation of each statement will be a statement about discontinuity. However, for convenience, we just establish the most common statement here. A function f is discontinuous at point C even only if there exists a sequence Xn in A, Xn approaching C, but f of Xn not approaching f of C. So this is essentially the negation of the sequential criterion that we established earlier. This is very common because remember, we spent a lot of time discussing sequential, the convergence of sequences. That's why we know this topic very well. Now we have the following definition. We say that a function f is continuous on the set B, a subset of A, if it is continuous at every point of B. So basically, continuity is a local property. It is defined a point, and then you can extend that definition to a set. Now we're going to see some examples. The function fx is constantly equal to a constant b. Then obviously we have the limit when x approaching c of the function f of x equal to the limit x approaching c of the number b, which equal to the number b, and that is equal to f of c. So the function f of x here is continuous at any point c in a set of all real numbers. That's why it is continuous on the set of real numbers. Another example is the function gx equal to x. By the result of chapter 4 we discussed earlier, the limit of the function g of x when x approaching c is equal to the limit of the function x when x approaching c, which is equal to c, and this is exactly equal to g evaluated at the point c. That's why the function f of x here is continuous at any point c, and consequently it is continuous on the set of real numbers. Another example is the function f of phi of x equal to 1 over x. This example is a little bit more involved. For c greater than 0, we already knew from chapter 4 that the limit of the function phi of x when x approaching c is going to be equal to 1 over c, and this is equal to phi of c. So the function phi here is continuous on the set of all positive numbers. At 0, the function is not defined. That's why the function is discontinuous at 0. It's not even defined. Actually, the function phi of x here is continuous at any number different from 0. That is, it continuous on a set of numbers c with c different from 0. And furthermore, we observe from chapter 4 that the limit when x approaching 0 from the right is equal to plus infinity, and the limit of the function phi when x approaching 0 from the left equal to minus infinity. So the diagram here gives you a visualization of the graph of the function phi of x. Another example of a discontinuous function is the function psi of x. Remember, this function is defined to be 1 for positive numbers, -1 for negative numbers, and 0 for 0. In this case, the function is defined and equal to 0, but the limit of the function when x approaching 0 does not exist. We recall that the limit when x approaching 0 from the right equals 1, and the limit when x approaching 0 from the left equals -1. That's why the limit of the function when x approaching 0 is not equal to the value of the function at 0. So that example actually motivates the following discussion about continuous extension. Maybe instead of defining the function psi of x in that way, we can try to make other functions continuous appropriately. Consider the function f of x not defined at the point C. However, if the limit of the function f of x equal to L when x approaching C, then we can define f of x in the following way. So this is the function capital F of x to distinguish it from the function small letter f of x. This function is given as follows. This equal to the ordinary function f of x, small letter f of x, for x different from c, and is equal to L for x equal to c. In this way, the function capital F of x is continuous at the point C. Here is an example. We consider the function f of x equal to x squared minus 4 divided by x minus 2. Remember, we cannot divide by 0. So immediately, we observe that this function, small letter f of x, is not defined at 0. On the other hand, we can consider the limit when x approaching 2. And as we observe in chapter 4, we can simplify the algebraic expression here so that the denominator is cancelled out with a factor in the numerator. That's why the limit here equal to the limit when x approaching 2 of the function x plus 2, which equal to 2 plus 2 equals 4 by a theorem in chapter 4. Consequently, we can define the function capital F of x in the following way. It's going to be equal to the function small letter f of x if x different from 2, and it's equal to 4 if x equal to 2. In this way, the capital F of 4 is exactly equal to the limit of this function when x approaching 4 but not equal to 4. Therefore, the function is continuous on the set of real numbers. In the next section, we're going to discuss combination of continuous functions.